So I'm going to talk about some of the planning solutions that we've come up in our lab involving deep learning and deep RLs. So I'll get to that. So what I wanted to do is start out thinking about, we've heard all the hype, and I did a quick search of what deep learning is solving these days outside of robotics, and it's going to solve cancer and tell us what the stock market's going to happen to the impact of COVID-19. And I don't know if you knew, I was not aware that it's going to actually solve our bread from molding very well. So our questions always like that we get is, why hasn't it solved planning? And I think the talks this morning have been great to set up why that is. I actually did a little bit of searching to see what planners thought before this actual workshop. And we saw, this article just came out as an interview with Gill and Wolfram. And what they were talking about is how deep learning really still has a long way to go to solve these problems in planning and trajectory generation. And like what we saw, and that like relies into all the task and motion planning, task planning that we've seen this morning too. So some of the big questions that they brought up has been things that we've been discussing this morning, which is pretty exciting. The deep learning really needs to be applied to problems it's good at, classification, function, and prostration, rather than trying to throw it at the entire problem that we have in front of us. And this I thought came back to Jeanette's point this morning, that we're still trying to how best to use learning within these problems. We're still trying to figure out where to apply it, how to apply it, and where it works good. And it's good that we've seen so many different solutions to that today. One thing they did bring up, which I didn't agree with, and I'm glad the point of this workshop has really been to not kind of do this, is to think about how learning and planning really interplay. They think of them as two separate components, but I do think that's not necessarily the way to go. And hopefully we'll see that from my talk too, and the other ones we've seen already today. And also, what I'm going to add that they didn't mention that, and this will play into what Sergey and Lydia were discussing on the chat, is that it's also critical to understand how that learning impacts the planning, because we've seen in our own research how there may be a mismatch there, and we have to actually understand that impact very well, especially if the application is very critical. So we know, I had to put in a slide to you, Thomas. I'm looking at you because you're on my screen over here. But that all interesting planning is hard, even from the earliest work in motion planning. There's a lot of hard problems in here, even just figuring out when I'm moving between two configurations, what is that volume that I need to sweep from one to another? And this has been a long existing problem that's existed in planning, and it's still very difficult to compute. And it's good that we have some nice approximate solutions. I know I didn't shout out to Lydia here too, in terms of solving this problem more efficiently. So things like sampling-based motion planning, which give us a very approximate way of quickly figuring out a plan for things like these high-dimensional linkages, where if we try to do it completely, these swept volumes get very expensive. So we can do things like sample the configuration space. That's how the probabilistic roadmap works really quick. We just sample configurations. Some are valid or not in collision. Some are invalid or in collision. But the next step gets a little bit expensive, or it could, where we want to find pairs to connect, and we want to find ones that are likely to succeed. And it's important to do that. It can be important, especially in task planning, when we're kind of working in these narrow spaces, where we want to figure out pairs that are very likely to connect. And so we can identify them, and then we can local plan between them, sometimes just with a straight line interpolation, and then we can find a route where we need to go. So even one of the primitive operations in here in the sampling-based motion planning can turn out to be pretty expensive. How do we even pick these states to connect? It's an n-square computation. Yeah, we can use approximations. There's a lot of different ways to do this, but it can be, this primitive can actually be pretty expensive. So one thing we've looked at is how to kind of, how to best do this, solve this problem. And let's take this robot arm and think about it for a second, where a robot arm has two joints, and it has to move between two configurations, this one and another one. And it's going to move, that's going to take the amount of space It's going to move between those two configurations. And if we do solve this in the typical efficient manner, we would use a Euclidean distance metric, something like this, where we just calculate the distances that change in the joint angles. So this would be a 90-degree change. But if we also look at a different type of motion, something like this for this linkage, then we have the same 90-degree change, but it's a much smaller motion than before. So what we've seen is if we're trying to find these likely connections, that swept volume is actually very ideal. If we're using a straight line interpolation to get between two nearby configurations, swept volume is really great. But it's been shown to be very intractable for this kind of idea of sampling-based planning, because we have this n-squared operation and lots of configurations to test between. So if we want to use this, there's been other solutions to learn a weighted Euclidean, so we can learn a set of weights to figure out what joints impact most to approximating that swept volume. Or we have been looking at, in our lab, how we can actually learn the swept volume directly. So it's a pretty easy problem. That's why I picked it to start out with for this talk, is that we just take in two configurations. And we learn the actual swept volume scalar value. I know I have a picture of the swept volume there on the right. And, but we're gonna learn that, actually start out just by simply learning the scalar value so we can use it to compare configurations to see which ones are expected to move shorter distances, so that we can kind of build this roadmap in this incremental fashion and use those pairs that are most likely to connect. So how does this work? We watched it over learning. So over learning, we can, since it's a supervised learning problem, super easy to watch, we can check the loss in the expected value over the predicted value and over the training. And what we see is that we have neural networks that learn to predict swept volume, or at least on that training set, very well. And here is also the weighted Euclidean, which learns, but it also doesn't approximate the swept volume very well. So we can check the accuracy once we build a model, how well we are able to predict those swept volumes. And we can see, compare those with configuration pairs, predicted swept volumes for configuration pairs versus the actual value, compared to our Euclidean and our weighted Euclidean that are typically used. So if they match, they should fit right along this black line. And what we see is Euclidean does fairly well, but it's also very dispersed in terms of predicting swept volume. Weighted Euclidean doesn't learn it learns better, but not super great. And then we also have a deep neural network being able to predict swept volume very well. So this goes back to the beginning, where we're looking for problems where deep learning works really well in terms of doing this very nice continuous function approximation. It's a very easy problem for it to learn. So we came to a point where, well, we want to use this to actually manipulate objects in very tight spaces and figure out what actions we can take very quickly and filter out those actions quickly. And what we've been looking at is, rather than predicting just the scalar value, can we actually predict that geometry that's expected for a particular motion? Well, this takes a pretty different structure, where we need to represent that output, that representative geometry of the swept volume. And we can think of it, one of the easiest ways to think about it is a cubic representation, where cubes can be occupied or not occupied, whether or not they're taking up some of that swept volume space. So our neural network changes for this type of setup, where we still do just take in two configurations, but the output is very different, because we can think of it as a series of voxels where either they're occupied or not occupied. It's inspired by decoder-like networks. And then we can train it on pairs just like before, but now we're learning the geometry. And here's an example of a configuration pair and the true value and a prediction and the errors between those two systems. So we've got false negatives and false positives in there as well. So this learning seems to work really well. We tested it on lots of robots, but this kind of gets back to my fourth point, is really thinking about what that learning is doing to our planning, both for motion planning and for task and motion planning. And if we're trying to fit in tight spaces, these errors actually could be pretty critical in terms of telling us things about overestimations or underestimations about the sweat volume that we're predicting. So we actually had to look very much in detail as to where these errors were occurring, if they're occurring near the surface or further out. And luckily for the systems, most of the systems they showed, there was one exception, the planar was very difficult, is that the errors were within 3 voxels of the surface, most within 1 voxels. But depending on the application, this could be a problem. So we also looked at, which I'm not going to show in our short talk, a tunable measure so that we can actually tune it for different applications when an overestimation or underestimation is more needed. So I actually want to spend a little bit of time thinking about different applications as well, besides just the sweat volume that can be incorporated into that sampling-based motion planning, but also about how we can learn other control problems, kind of like we've been talking about in some of the other talks. And if we have a robot that needs to navigate over long distances like this, we need to figure out how to learn some representation so he can start to navigate. So this brought us to an idea of using DeepRL to learn how to control that robot in a small scale. And then we'll see how that integrates into planning in order to do these longer range navigation goals like we've been talking about in some of the other talks. So we have our robot, and he's going to observe things about the world, and then he's going to get rewards depending on what status he's in, and then our DeepRL is going to just learn that policy. And Sergey talked about there's lots of different ways to do this. We just, again, picked one that seemed to work well for this problem. We have a small environment that he learns in, so he's learning these short-range navigation tasks. And his reward is to avoid obstacles and get to a nearby goal. So he's just doing short navigation. And then our observations are just his LiDAR sensors and the goal location, and they actually have some noise integrated into them as well. Now, I agree this doesn't answer some of the questions we've been having in some of the other talks about how to integrate noise into our systems or different, but it does, for this type of application, it did actually work really well. Okay. So he learns in this small space, he learns how to navigate small, but we need to actually get him to navigate in a larger space. And this is actually one of the floors from Google where they have like very long distances. It's a very large floor. And what we can do is actually pretty simple. We can actually do sampling-based motion planning like before, where we sample states within these models of these worlds. But then we take our pre-trained RL agent, which knows how to navigate over short distances, and use that to do this local planning or this connection between samples, where we can start to integrate some of the expected noise from the sensors or some expectation of whether or not that robot can actually achieve that motion. And because we have this uncertainty, there comes into play where we need to actually test edges multiple times within the planning. So we're going to add an edge only if that RL agent can consistently navigate between those 2 nodes. And this really gives us that ability to, even though we learned in this small space, execute really long trajectories within that bigger space. This is just a few of those examples of trajectory over the long space. And once we actually plan and we think we know how the robot will move, we actually use that AI agent to execute the plan. You'll see a little bit of inconsistency in there. Some of it is from drawing from the PRM, but mostly it follows the path. We did find that this was actually picked up to be highlighted in the Google AI blog. So this is the robot executing within the Google floor. I didn't want to take the risk of video issues, so I put the link there if you're interested. There were some changes in the environment, and because it had this robust, we call it like a local planner, being able to control in this local space, it actually was able to adjust on the fly for that as well. Okay. So I wanted to spend my last few minutes talking about not just what kind of is the big picture of this. And I do think we've been asking this question, Jeanette brought it up this morning, Gil and Ruffer brought it up in their article, is what are those, how do we use learning to best solve this problem? And I do think we're gonna keep coming up with amazing solutions for this, even our lab, we've been just coming up with new applications to integrate the learning directly into the planning, and so we can find better solutions for really hard problems. And here we've got two examples. One on the left is moving obstacle avoidance with sensor noise, and also here with an easy modification, which to my students means 2 months of work, but we can do interception of moving obstacles instead of moving obstacle avoidance. So so we can ask lots of questions and start integrating learning in lots of different ways. But I think from the planning perspective, our bigger question is now this kind of question 4 is, how is the learning actually impacting the planning? So what is the learning actually doing to the guarantees, the functionality, that planning that we are not necessarily aware of, or we have to work a little bit harder to be aware of? So here we have, we've talked about it in these two applications, where if we have sweat volumes, we can have overestimations or underestimations of the volume that are integrated, and how that, we can actually think about how that can impact our planning. We explored it a little bit more in depth in the paper, because if you have an overestimation, things can be not possible, marked as not possible when they are. Same thing, or opposite for underestimation. And then if we have uncertainty integrated, we have that we have integrated directly in the planning. We have a model of how we expect that robot should be able to move directly in the planning phase. So it should make it easier for it to execute when it's actually execute with uncertainty when it's actually executing that plan. So we've actually seen this in some other applications where it's been a little bit, been even actually more critical, safety critical for the system, where maybe we have a moving obstacle. So this is a circular moving obstacle, moving in a plane, in a linear trajectory, and it's moving deterministically. And so we can map out exactly what our collision probability will be for being in any state within this, this problem. And we can also learn this problem as well. We can start learning how to interact just from observations of this obstacle, learn what the value is of being in any states. So just like Sergey was talking about, kind of learning that value function and maybe using that to drive how we're moving as well for different types of problems. So here we have the value function, but it's actually turned into a collision probability, so the two plots can be relatable. So you have you have red being a high collision probability and blue being low or no collision probability. And so we see that they're similar. The learning is working really well. If we look at the standard measurements of success, kind of like we did in the sweat volume, things like loss, things like survival rates, this solution works really well, but we see it's not actually learning the true formal solution, which it's learning. We don't expect it to. But we can also look at how that impacts the planning. So the other nice thing is we can get the policy out, where we can know what actions we should take given the states in this world. And for the optimal problem, we can only get policies for being right in front of the obstacle. It's like take the nearest exit or move away from that obstacle. All the other dots are equal value. So it's only telling us in front. From our learning solution, we're going to get policies from every state just because it's doing an argmax. So you're going to see a lot more arrows. But most of the arrows seem to make sense. We can chase after the obstacle because we're going slower than it. Here at the back, around it, we're going around it. But here in the front, it's doing actually something unexpected. Perfect. It's doing something actually unexpected, where it's telling you to run away from the obstacle, like the obstacle in the, like the monster in the horror movie, and you're running right in front of it, but you're going slower than it. And this is not a good control strategy. But in practice, the learning says it actually works really well. So this is kind of the things that we need to look at, and I do agree with Lydia's comments in the chat, is that maybe we don't necessarily want to use this directly for planning, but also we can use the value function to help drive sort of local decisions with the planning, with some understanding that there may be discrepancies in there as well. Cool. So I was wrapping up. This is, I'm so glad I was able to come today. We realized in the lab, this was not my work. This is work of my students. They are amazing. And our collaborators at Google Brain and our lab alumni, we realized in the pandemic, we had no recent lab pictures. So I commissioned a cartoonist to do these pictures of my lab. So we really want to thank them for all their hard work on this, and then our funding agencies that have helped support the work